Good morning, everybody, and welcome to the CEIA Maths Tutorials Online. This week we have differentiation with John Forrest.
Good morning, everybody, and you're very welcome this morning to our talk on differentiation. Today's plan is we've about 60 slides, and all of them are numbered, so you can see at any given time how much progress we've made. The entire duration is going to be approximately 2.5 hours. We will take 2 breaks, and they'll be about 10 minutes each. Also, I can stay on afterwards, and I welcome any questions and feedback. And in addition, you can, if you have any questions while I'm talking through this, you have a Q&A button, I believe, and Eamon and will be able to communicate those questions to me or be able to answer them themselves via text. So for this, it'll be really helpful if you have to hand log tables, a notepad and a math textbook. You won't need them too much for the first section, but for subsequent sections, they'll be potentially very useful to you. And also, if you have any questions afterwards, if you want to, when you're reviewing your notes or something over the next couple of days, you can send an email to info@ceia.ie, and if you include differentiation in the title, that email will find its way to me and I'll be able to respond to it. So to jump off, what is differentiation? So in mathematics, differentiation examines functions, and it determines the rate of change of the output value y with respect to the input value x. And so here's a simple graph of a function. It's a straight line. And so we know that the equation for a straight line is y is equal to mx plus c, and we know therefore that the slope is m. So this tells us that the rate of change of y with respect to x is m. So the slope is equal to the rate of change. However, for lines, determining the slope is fairly simple, but there are other more complex functions, like the ones that I've graphed here, where determining the slope is not as easy to do. And so we need to figure out a way of doing that. And differentiation is the tool that enables us to do this. When we differentiate a function f of x, we get a new function f dash of x, which is also called dy dx. There's some different notations there, and we'll be going through that in a bit more detail as we go along. But for now, all you need to know is f dash of x and dy dx are the same thing, and both of them are a function that gives you the slope of the original function. So f dash of x is a function that's derived from f of x, and so it's sometimes called the derivative of f of x. F dash of x is a function that tells us the slope of f of x at every point on the curve. So here's a kind of a graphic that explains what we're trying to do. What you've got on the left-hand side, you've got some function that is of interest, and we're looking for a method or a process, and the output of that process is the slope function, and the slope function is f dash of x or dy dx. It's a function that tells you what is the slope of your original function at every point. So the input, as I've mentioned, is f of x, which is some function of x, and the output is f dash of x, which is also called dy dx, and that's a new function, and that new function tells us what the slope of f of x is for any given value of x. Since f dash of x is a function, we can differentiate that as well, and we will be touching on this later. So before we start on how we find out how to differentiate, we need to have a quick note on limits here. So we need to understand limits before we can go on to differentiating. So let's look at this function. F of x is equal to x squared minus 1 all over x minus 1. And that's a graph of the function. But the problem with this function is when x is equal to 1, you get 0 above the line and 0 below the line. So the value of the function is not defined at that point. There's, as you can see in the picture, there's what you would call a hole almost, where at just this one point where x is equal to 1, we can't evaluate what the output of that function is. So however, there is a way to get around this. So first of all, we can allow x to get as close to 1 as we want. We can approach 1 from the left or from the right. So we can approach 1, or we can approach 1 from the left-hand side, and we can also approach it from the right-hand side. From the left-hand side, we're going up the line. From the right-hand side, we're coming down. And we can see that as x approaches 1, f of x approaches 2. So we can see that graphically. And from a notation point of view, we say that the limit as x goes to 1 of f of x is equal to 2. That's how it's written. So we can also note that x squared minus 1 all over x minus 1, that's equal to x plus 1 by x minus 1 all over x minus 1. And that's equal to x plus 1. So we know that f of 1 is actually equal to 2 in this case, because we've been able to do some factorization and simplify the equation. So in this case, and this is a very, very important point, f of x is exactly equal to the limit as x goes to 1 of f of x. So we might think that as we're allowing x to get closer and closer and closer to 1, we're getting a better approximation of what the value of the function is at x equal to 1. But if we use limits properly, you're not getting an approximation, you are getting the exact actual value of that function at that point. So we use limits when we can't evaluate the function directly for certain values of x. And when we use limits correctly, we will get the exact value that we need. Now, there are some functions where you can't get limits, or there are some functions where limits don't exist at certain points. But generally speaking, if the limit exists, the result of finding the limit is an exact value. And the last note that I'd like to make here is that you can have this idea of the limit as x goes to infinity. Now, x cannot approach infinity because no matter how big x gets, infinity is still very, very far away. But we can make x as big as we like. And so this concept of the limit of x going to infinity is valid. So really the kind of single takeaway line from this is what I've highlighted in yellow here, is that f of x at a certain point, the value of f of x is exactly equal to the limit. So to move on, we can now start to think about differentiating from first principles. So let's say we want to find the slope of a curve C at some point A. So our curve C is in red here, and A is down at the bottom of the, let me just get my pointer going here. I think this is it. Yes. So this is the point A, and we want to find the slope of the curve at this point. So our first estimate is to draw a line, which the secant line, AB, and a secant line is just a line that cuts through a curve like this one does. And slight problem here with this. I wonder if... So now the next step is to pick a point B dash, which is closer to A. And this, you can see our new blue line here. This gives a better estimate of the slope. You can see that the new blue line has a different slope to our original one, and that slope is closer to what the slope is at point A. And as we keep moving B dash towards A, the estimate gets closer and closer to the actual slope of C at A. So how do we show this mathematically? Well, here's an animation that helps to explain what we're trying to do here. So if I move, as I move the slider here, you can see that the hypotenuse of this triangle gets shorter and shorter. But if you look at the slope of it, when I make the triangle bigger, the slope changes, and the slope is quite different from the slope of the blue curve at 1, 1. But if I make that triangle smaller and smaller and smaller, you can see that the slope of the hypotenuse is getting closer and closer and closer to the slope of the curve. And when I make it, like right now, it still isn't quite perfect, but you can see that the slope is a much, much better approximation than, say, when the triangle was large like this. So we just keep making this triangle smaller and smaller and smaller and smaller. And essentially in the limit, as the length of the hypotenuse goes to 0, in that limit, we get the exact slope of the curve at that point. And so you may be interested, if you want to look at this yourselves after, this is on a website called GeoGebra. I think you can see the logo there in the top left corner. And so you might want to, and I think if you search for Tom Carpenter, who's the author of this, you will find the page with this little applet on it, which you can examine yourself afterwards. Okay, so getting back to the presentation. So we start off with our triangle like we've just seen in the animation, and you can see that here, I'm going to use, at this point you have x and f of x, and up at this point here you have some value x plus h and f of x plus h. And so the base of the triangle, the length of the base of the triangle is h, and the length of the vertical side of the triangle is f of x plus h minus f of x. And so the gradient, the slope of our hypotenuse, is f of x plus h minus f of x all over h. So the slope of the line, so that's the slope of the hypotenuse, that's y minus y1 all over x minus x1, and that's equal to f of x plus h minus f of x all over h. So we want to find the slope of this line as h tends towards 0. Remember, we want to shrink h, we want to make h smaller and smaller and smaller, so that the hypotenuse gets smaller and smaller and smaller, and the slope of the hypotenuse gets closer and closer and closer to the slope of the curve at the point x. And so this, the slope as h tends towards 0 is this limit. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. And this is why limits are important. It's a crucial part of the differentiation process. And so the animation link that I just mentioned in that line here, that's the animation that I've just shown you. So let's define notation and language a little bit. So we're saying that dy dx is equal to f dash of x, and that's the limit as h goes to 0 of f of x plus h minus f of x all over h. This can be called the derivative or the first derivative of y with respect to x, because it's derived from f of x. And dy dx, which is equal to f dash of x, gives the slope of the tangent to f of x at the point x. So some notation then if y is equal to f of x, then dy dx is equal to f dash of x. But we don't always have to talk about this in terms of y and x. And in fact, we can call functions or variables anything we want. So like if u is equal to some function g of x, then du dx is equal to g dash of x. So we kind of don't care if the variable is called y or u or x, as obviously as long as we don't mix them up. So we're now ready to start differentiating from first principles. And so differentiating from first principles simply means using the limit of f plus h minus f of x all over h. So let's look at a simple example first of all to see how we do this. So here we've got f of x is equal to 5x plus 3. It's a line. So f of x plus h then, that's equal to 5 of x plus h plus 3. We simply substitute the x plus h for x. And f of x plus h minus f of x all over h then becomes 5 of x plus h plus 3. And then we subtract f of x. And so we're simply left with 5h all over h, and that's 5. So dy dx is equal to f dash of x, and that's equal to 5 in this case. And so this is our first time doing this for many of us. So let's ask ourselves, does this make sense? It's been a very simple case. We didn't even have to evaluate the limit. But is it the result that we expect? Well, I would argue that it is, because f of x is a line expressed in the form y is equal to mx plus c. F dash of x is equal to m, the slope of the line. And you can see from f of x is 5x plus 3, so m is equal to 5. And we're saying dy dx is also equal to 5. And we've been able to calculate what dy dx is. So far, so good. Here's a second example. So here we're going to look at a quadratic. It's f of x is equal to 3x squared minus 5x plus 12. So f of x plus h then is equal to 3 into x plus h all to be squared minus 5 into x plus h plus 12. And so, I've, in this particular slide, anything to do with f of x plus h is colored in red here just to help follow it a bit more easily. Excuse me. So we want to find f of x plus h minus f of x all over h, as we did before. And so you can see the 3 into x plus h squared minus 5 into x plus h plus 12, and then minus f of x, that's minus what I have in brackets here, minus the 3x squared minus 5x plus 12 all over h. And so let's look to simplify that a little bit. And so really all I'm doing here is just doing the algebra workings. And we can see that when we multiply everything out, we can start knocking off the x squareds and the x's, and the 12s cancel. And so that leaves us with 6xh plus 3h squared minus 5h all over h. And that becomes 3h plus 6x minus 5. So now we do have to take the limit, because we've got a h in there and we need to let the h go to 0. So the limit as h goes to 0 is simply 6x minus 5. And so dy dx is equal to f dash of x, and that's equal to 6x minus 5. I'm just going to pause there for a second if you want to make any note or to take a screenshot or something. Note also, I just remind you that this will be available on YouTube afterwards, so you'll be able to review it there as well. So in this case, what I'd like to do again, just circle back and see, does this make sense, like we did with the first problem? So we want to compare f of x with f dash of x. And so here we have a graph which shows f of x is in red, that's 3x squared minus 5x plus 12, and f dash of x is the blue line, which is 6x minus 5. So let's look at, see at this point here, the slope is 0 on f of x, and you can see there's a dashed black and white line going down, and you can see that the value of f dash of x is also 0. So this looks reasonable. F dash of x is 0 when the slope is 0 at f of x. Here on the left-hand side of the curve, we can see that it's a large slope, and the slope is decreasing and it's negative. So what I mean by this is, as you move to the left, the magnitude of the slope gets bigger. The slope gets more and more negative, and it's quite steep. And similarly, if you look to the right-hand side, you can see the slope is large, the slope is increasing, and the slope is positive. And just looking at this visually, f dash of x seems to fit in pretty well with that. You can see on the right-hand side, f dash of x climbs steeply. The value of f dash of x increases rapidly, just as the slope on f of x increases rapidly. And you can see on the left-hand side, the value of f dash of x decreases rapidly, just as you move to the left, the slope of f of x gets rapidly more negative. So again, so far so good. So I would encourage you to do some practice on differentiation from first principles. It is a questionable topic, but differentiation from first principles gets laborious, especially for more complicated functions. It is possible to differentiate, say, sine x and cos x from first principles, excuse me, but it's a fairly significant amount of effort. There's about half a page to a page of math to get from start to finish there. And so in order to help us to work more efficiently, we use rules. So we're going to move on from differentiation from first principles now, and we're going to talk about what are the rules that we use to enable us to work more quickly. So here's some rules with some examples. So if y is k times f of x, dy dx is equal to k times f dash of x, where k is a constant. So here's a very simple example. If y is 15x, dy dx is 15. Just as if y was x, dy dx would be 1. If y is 15x, dy dx is 15. If y is k times x, dy dx is equal to k. You're simply, if you're differentiating a function multiplied by a constant, you just differentiate the function and multiply your answer by the same constant. If y is x to the power of n, then dy dx is n times x to the power of n minus 1. And a very simple example here is if y is equal to x to the power of a half, dy dx is equal to half of x to the power of minus a half. So you simply take the half, which is the power of n, and then you change the exponent of x to n minus 1. So from this rule, it follows that if y is equal to k, then y is equal to k times x to the power of 0. Now, x to the power of 0 is always 1. But if you differentiate x to the power of 0, you get 0 times x to the power of n minus 1, which is also 0. So dy dx is still 0. And so the derivative of a constant is always 0. And you can show this graphically as well. If you do a sketch of the line, say, y is equal to 5, which is a constant, the slope of that line is 0. So here's the sum rule then. This is where we talk about if y is equal to u plus v. This is where u is a function and v is a function. So if y is equal to u plus v, dy dx is equal to du dx plus dv dx. And so a simple example here is, let's say y is equal to 7x cubed plus 3x squared. 7x cubed is a function. We can say 7x cubed is the u function. And so when we differentiate 7x cubed, using the two rules above, if you differentiate x cubed, you get 3x squared. You multiply that by 7, so that gives you 21x squared. And then similarly, if you differentiate the second piece, the 3x squared piece, differentiate x squared first, and that gives you 2x, and then you multiply that by 3, and that gives you 6x. There's a product rule then, which is if y is the product of two functions, dy dx is equal to u dv dx plus v du dx. And we'll do an example of that one fairly shortly. There's a quotient rule where if y is equal to u divided by v, dy dx is equal to 1 over v squared into v du dx minus u dv dx. And if you've got a maths book or a log table or something available to you, I'd recommend that you open or find the page. I think log tables might be better because they list all of the rules in a single page, and so you will be able to refer back to those as we continue our discussion here. The final rule I want to talk about is the chain rule, and that states that if y is some function of another function of x, then dy dx is dy du by du dx. We will certainly be doing examples in that shortly. You just need to know for now that the rule exists, and ideally have it available in front of you on a log table or something like that. So note, u and v, dy dx, dv dx, du dx, these are all functions, and y is a dependent variable. That means it depends on the value of x, and rules can be combined. So you can combine the chain rule and the product rule and the sum rule as appropriate, depending on the nature of the problem that you're trying to deal with. So here's a product rule example. Now, this is quite a colorful slide, but I'm just trying to, so here dy dx is white, u and it is red, dv dx is blue, v is yellow, and du dx is green. It's just, I tried to color it in this way just so that hopefully makes it a bit easier to follow. So if f of x is equal to 3x plus 4 by x minus 2, which is uv, we're saying that the u piece is 3x plus 4, the v piece is x minus 2. So, and du dx is equal to 3, and dv dx is equal to 1. So f dash of x then, it's the first piece here is u dv dx, so that's 3x plus 4, which is u, multiplied by 1, because we've said that dv dx is equal to 1. And then to that we must add v du dx, and so v is x minus 2, and du dx is equal to 3. So when you multiply those out and add them, you get that f dash of x is equal to 6x minus 2. So here's a similar example for the quotient rule. So again, using similar colors as before, if y is equal to u divided by v, dy dx is equal to 1 over v squared multiplied into v du dx minus u dv dx. And so here's an example using the similar color scheme. So if f of x is equal to 3x minus 2 over x squared minus 3, u, which is equal to u over v, du dx is 3, and dv dx is equal to 2x. So f dash of x then is, we put under the line, we put v squared. So that's where the x squared minus 3 all to be squared, that's where that comes from. And then over the line, you've got v du dx. So that's x squared minus 3, which is v, multiplied by 3, which is du dx. And then from that, we subtract u dv dx. And so u is 3x plus 2, and dv dx is equal to 2x. When you multiply all those out and simplify it a bit, your answer is minus 3x squared minus 4x minus 9 all over x squared minus 3 all to be squared. Okay, so let's move on. So here's an example of the chain rule. And just a reminder of the rule. If y is some function of u of x, then dy dx is equal to dy du multiplied by du dx. So let's look at an example. So y is equal to 3x plus 4 all to be squared. So we're going to let u be equal to 3x plus 4. So du dx is equal to 3. And if u is equal to 3x plus 4, then y is equal to u squared. So dy du is equal to 2u. And dy du by du dx then, which is equal to dy dx, that becomes 2u multiplied by 3, which is equal to 6u. But we said that u is equal to 3x plus 4. So that's 6 into 3x plus 4, and that's equal to 18x plus 24. Of course, we can do this another way. We can say, right, 3x plus 4 to be squared is equal to 9x squared plus 24x plus 16. And so dy dx very simply is equal to 18x plus 24. And that's just a reminder of the power rule there. So for example, the 9x squared piece here, if you differentiate that, you differentiate the x squared, that gives you 2x, and you multiply that by 9, and that's where the 18x comes from. The 24x, when you differentiate that, that's x to the power of 1. So it's 24 times x to the power of 0, which is 24, and then 16 is a constant. So when you differentiate that, you get 0. The point here is that we've shown a simple example of using the chain rule, and we've also been able to multiply it out and differentiate it using in a more simple way, but we're still getting the same answer. So it's consistent. So either approach is valid, and it's always good to be able to check your own work. So if you're doing chain rule problems like this when you're starting off, it can be helpful to multiply them out or otherwise simplify them. Some of the initial chain rule examples in your textbooks don't necessarily need the chain rule, but they're a way of practicing the chain rule so that you can handle more complex problems. Generally speaking, for more advanced problems, the chain rule is often the best and perhaps the only way to find a solution. So the chain rule is really, really important, and it is it's a very powerful rule and is really useful, as we'll see. So here's an example. Functions f and g. This is a slightly more complicated chain rule example, which we're going to look at in two different ways. So functions f and g are given by f of x is equal to 3x plus 1, and g of x is equal to x squared minus 2. So the first piece here is find p of x, where p of x is equal to f of g of x. So the p of x, so f of x is 3x plus 1, so f of g of x is 3g of x plus 1. And so now we substitute in for g of x, x squared minus 2, so that becomes 3x squared minus 6 plus 1. And so that evaluates to 3x squared minus 5. Similarly, q of x is equal to g of f of x. So g of f of x is f of x to be squared minus 2. That works out at, that evaluates to 9x squared plus 6x minus 1. So part B then, we want to solve p dash of x is equal to q dash of x. So we said that p of x is equal to 3x squared minus 5. So p dash of x is equal to 6x. And q dash of x then, we said that q of x is equal to 9x squared plus 6x minus 1. So q dash of x is equal to 18x plus 6. And if you solve this using a simultaneous equation, we get p dash of x is equal to q dash of x when x is equal to minus a half. And it might be an interesting exercise for you in your own time to get go to a graphing calculator website and graph those two functions and see where their slopes are the same. So an alternative then, using the chain rule, you can say p of x is equal to f of g of x, which is equal to 3g of x plus 1. So we already have that. P dash of x is equal to dp dg by dg dx, and that's equal to 3 by 2x, which is 6x as before. And similarly, for q of x, we can say q dash of x is equal to dq df by df dx, and that works out to be 18x plus 6, as we did before. The with with the chain rule, excuse me, no, 1 second, that's not working for me. I'm going to try. With the chain rule, really, the differentiation piece isn't that hard. The secret sauce is getting your variables right. So here we have p of x is equal to f of g of x. We want p dash of x, and it's dp dg by dg dx. Similarly, we've got q of x, which is equal to g of f of x. Q dash of x is equal to dq df by df dx. With practice, once you get fluent with the idea of how to use these variables, that is really the key to using the chain rule, and with practice it actually gets quite easy. So here's another chain rule example. If f of x is equal to x minus 1 over x plus 1, we want to find the value of f dash of 5 over 4. So we're going to let u be equal to x minus 1 over x plus 1. So y is equal to u to the power of a half, and dy du is equal to half u to the power of minus a half. And that becomes a half multiplied by 1 all over x minus 1 over x plus 1 to the power of a half. And so that's simply using the power rule. So that's the dy du piece. Now we want to find du dx. So du dx, then we use the quotient rule. So that's, and I've included the quotient rule here, it's 1 over v squared into v du minus u dv. So the v squared, v in this case is the x plus 1. So it's x plus 1 squared under the line. And v du dx. So it's x plus 1, which is v. And in this case, du dx is equal to 1. And then minus u dv dx. So u is x minus 1 and dv dx is equal to 1. So this all du dx evaluates to 2 all over x plus 1 to be squared. And so dy dx then is dy du by du dx. And we simply, we multiply all this stuff out and simplify, and we get our result. And then to find f dash of 5 over 4, we just plug in 5 over 4 for x, and this all evaluates to 16 over 27. And in fact, on the previous line, you can see I didn't bother to multiply the two terms here because I didn't need to. All I needed to do was substitute 5 over 4 for x in each of those two terms and then multiply it out, which is a simpler way to do it, and also potentially less error prone as well, because multiplying out algebraic terms like this can get a bit tangled up looking, and it's easy to make a simple error that leads to the wrong result. So that's the chain rule. The next thing we're going to move on to is the differentiation of trigonometric functions. There are rules in the log tables for that. So if f of x is sine x, f dash of x is equal to cos of x. If f of x is equal to cos of x, f dash of x is equal to minus sine of x. If f of x is equal to tan of x, f dash of x is equal to sec squared of x. And from the chain rule then, if f of u of x, if you've got the cos of some function of x, f dash of x is equal to minus sine of u multiplied by du dx. So if you look at, if y is equal to cos u, we're simply saying dy du is equal to minus sine u, and we just need to multiply that by du dx. Similarly, if f of u of x is equal to sine of u, then the dy du piece of that is cos of u, and you multiply that by du dx to get f dash of x. And similarly for tan u, if f of u of x is equal to tan u, then the sec squared piece is the dy du piece, and then you just evaluate du dx. We'll be doing examples on this. So one final note, the sec of x, that function is 1 over cos of x. It's a function that I think most of us would not be familiar with up to this point, because generally speaking in trigonometry, we do not use the sec function. We generally use sine, cos, and tan. But in many of these problems with differentiation, we don't really care about what sec of x is. We just care about how do we differentiate tan of x. So some of the problems look more complex than they really are. And at this point, all you need is the rules, especially the chain rule, and some practice with these trigonometric functions. So to move on, here's a simple example, or first example of trigonometric differentiation. So we're going to say that y is tan to the power of 4 of 3x. So we're going to start off here and we're going to say let v be tan of 3x, so y is equal to v to the power of 4. And we're looking to find dy dx, which is dy dv by dv dx. So dy dv is equal to 4v cubed, which is equal to 4 tan cubed of 3x. And we now need to find dv dx. So remember, v is tan of 3x. So I'm going to let u be equal to 3x, so v is tan of u. We now want dv du by du dx. So dv du is equal to sec squared u, and du dx is equal to 3. So dv dx is equal to 3 sec squared of u. And so that becomes 3 sec squared of 3x, because we said that u is equal to 3x. And so dy dv by dv dx is equal to 4 tan cubed of 3x, because that's dy dv in red above. And that's multiplied by 3 sec squared 3x, which is the dv dx that's in yellow. And so dy dx is 12 tan cubed of 3x multiplied by sec squared of 3x. So just pause a moment there and sort of reflect on this. Trying to differentiate this from first principles would be, you can imagine that could be quite a chore. And so now you can see that by using the chain rule and the rules for trigonometric differentiation, we've taken a fairly complex, what looks initially to be a fairly complex function, and we've differentiated it in in just a couple of lines. Here's another example. So if y is the sine of x all over 1 plus tan of x, find f dash of 0. And so I just put the u over v rule here because we're going to be using that rule. So f dash of x, so we're saying that v is 1 plus tan x. So on the bottom line, we've got 1 plus tan x all to be squared because that's v squared. And on the top line, we've got v du dx. So that's 1 plus tan x, which is v, multiplied by cos x, which is du dx. And then from that, we, in the next pair of brackets, we've got minus u dv dx. So that's f dash of x. And we've done it in one line, which is nice. And then for f dash of 0, well, the tan of 0 is 0. The cos of 0 is 1. And then the second part vanishes because the sine of 0 is 0. So we get 1 plus 0 multiplied by 1 all over 1 plus 0. So f dash of 0 is equal to 1. So we also have inverse trigonometric functions. And here, the rules for those are here. So the sine minus 1 of x over a, that is, you read that as or arc sine or inverse sine of x over a. And similarly, for tan, it's arc tan or inverse tan. So let's say you get the sine of an angle, and let's say the result is x over a. The inverse sine of x over a takes you back to the original angle. So it's just an inverse function. And so again, I don't think I need to read all of these rules out. We just need to, as we've done up to now, we have our rules. We just need to learn how to apply them. And this may sound like cheating if you might, from a pure mathematics point of view, but as an engineer myself, I use mathematical rules regularly all the time without even questioning them. And really, we're you might say we're standing on the shoulders of giants here. A lot of work has been done to get to this point and give us these tools. And these are the tools that we use. So let's differentiate y, which is the arc sine of 2x. And so the rule here is f dash of x is equal to 1 over a squared minus x squared. So here a is a half, because if x over a is equal to 2x, then x has to be a half. And so what you do is you just plug in the value of a half wherever you see a. So you get 1 all over. So then a squared becomes a quarter minus x squared to the power of a half. And result, we've differentiated it. We're done. That's using the rule. Alternatively, using the chain rule, you can say y is equal to the arc sine of 2x. Let u be equal to 2x, so du dx is equal to 2. And so we have y is equal to arc sine of u. So dy du then is equal to 1 all over 1 minus u squared to the power of a half. That's equal to 1 all over 1 minus 4x squared, all to the power of a half. And then dy dx is equal to dy du by du dx. And so that gives you the same result as before. So sometimes you might just, you can choose to use the rule, the arc sine x over a rule, or alternatively, you can use the chain rule. For more complex problems, sometimes using the chain rule, some people find it a bit easier because it's a more step-by-step approach and you can follow the work that you're doing. For simpler problems, generally speaking, using the arc sine x over a rule or the arc tan x over a rule is quicker. So here's a more advanced example. If y is the arc tan of cos of x, we want to find f dash of pi over 6. And so the rule is if f of x is arc tan of u, f dash of x is equal to du dx by 1 all over 1 plus u squared. So that doesn't look too bad. So f dash of x then becomes, so cos of x is u, and so du dx is minus sine of x. So f dash of x becomes minus sine of x multiplied by 1 all over 1 plus cos squared x. And at x is equal to pi over 6, this evaluates to minus sine of x is a half. Cos squared of x is 3 over 4. And then when you evaluate that out, you get minus 2 over 7. Just a note there that sine of pi over 6 is a half, and cos of pi over 6 is root 3 over 2. So if cos pi of pi over 6 is root 3 over 2, cos squared of pi over 6 becomes 3/4. And that's where the 3/4 comes from in the red there. Excuse me, I have a little bit of a frog in my throat. So here's some questions to think about. Why is the derivative of a constant equal to 0? Is there anything we can't differentiate? Can sine of x be expressed as a polynomial? Why? And what about other functions like e to the power of x or the natural log of x? So quick reminder on polynomials. A polynomial is an expression with a finite number of terms, and you're allowed constants, variables, and powers combined using addition, subtraction, multiplication, and division. Okay, so that's a couple of questions to think about. We're going to take a break for 10 minutes. The next steps will be to review the questions that I've just put in front of you, and I'll go back to those in a second. We're going to be looking at how we differentiate logarithmic and exponential functions. We're going to talk a bit about tangents. And if you don't have one in front of you already, a logbook and or a textbook will be very useful for this next section. And so I'll just skip back to the previous slide so you can have a look at those review questions and maybe have a think about those, and we'll talk about those after the break. Thanks, everyone. So while we were on our break, does anyone have any thoughts about these questions that I've put up here? I think the first one is fairly easy. Why is the derivative of a constant equal to 0? In fact, we've already covered that. A constant can be expressed as k multiplied by x to the power of 0. And when you differentiate that using the power rule, it becomes 0. Or alternatively, you can graph the constant. Does anyone have any thoughts on the next question, though, which is a bit more interesting? Is there anything that we cannot differentiate? Or does anyone have any thoughts on the third question is, can functions like sine x or e to the power of x, can they be expressed as a polynomial? And why or why not? So, is there anything that we cannot differentiate? So here's a very simple function, and we can't differentiate it when x is equal to 0. And the function is y is equal to the absolute value of x. So the absolute value of x means if x is positive, then y is equal to x. But if x is negative, y is equal to minus x. So you get two straight lines like that. But what happens at x is equal to 0? What is the slope of the tangent to this curve at x equal to 0? And there are many lines that with many different slopes that you can draw through that point. So we say, sorry, 1 second, I pressed the wrong button. So at x is equal to 0, we said that this curve is not differentiable at x is equal to 0. And there are many, many functions that exhibit, you could say, odd behaviors or unorthodox behaviors with regard to differentiation. But generally speaking, we don't deal with those explicitly. We just need to be aware that they exist. Note also, we were talking about limits earlier. So you can see that while we can get the limit of this function, the limit as x goes to 0 of the absolute value of x is 0. But even though we can get the limit, we still can't differentiate it at that point. So to move on, can sine of x be expressed as a polynomial? Well, let's write out a polynomial like this, which is a0, which is a constant, and then a1 multiplied by x, a2 multiplied by x squared, a3 multiplied by x cubed, and so on. Well, if you differentiate it, the constant becomes 0, a1x becomes a1, a2x squared becomes 2a2x, and so on. So what has happened is we've started off with a polynomial of degree n, where the highest power of x is n. When we differentiate it, we get a polynomial of degree n minus 1. And if we keep on differentiating, the polynomial will eventually vanish. But if you keep differentiating, say, sine of x or cos of x, or those other functions. So if you differentiate sine, you get cos. If you differentiate cos, you get minus sine. If you differentiate minus sine, you get minus cos. You keep going around in circles. You can keep differentiating those functions forever. If you differentiate e to the x, you get e to the x. And we'll be talking about that in a minute. So the point is, those functions cannot be expressed as polynomials. And through differentiation, we can demonstrate that. So now we're going to move on to logarithms. There's a quick recap here, but really you need to have log tables or your textbook in front of you so that you can have to give yourself a quick reminder of the laws of logs. So real quick, if you multiply AB, the log of A of B is equal to the log of A plus the log of B, and therefore the log of A squared is equal to the log of A plus the log of A, which is twice the log of A. And from this, that should read the log of A to the power of n. The log of A to the power of n is equal to n times the log of A. Furthermore, the log of A to the power of n is true for all real values of n. And for division, then you've got the log of A over B is the log of A minus the log of B. And for powers and so on, you've got the log of 1 over A is equal to minus the log of A, which kind of makes sense because 1 over A is A to the power of minus 1. The log to the base x of x is always equal to 1. The log to the base x of 1 over x is always equal to minus 1. And the log of 1 to any base is always equal to 0. So we just move on. So we're going to talk about the differentiation of exponential functions. Exponential functions are functions that are based on e to the power of x. If y is equal to e to the x, dy dx is equal to e to the power of x. And e to the power of x is a very important function. It's a function that that comes up again and again and again as you go into more advanced math. It's a much more important function, for example, than sec of x is. If y is the natural log of x, no, the natural log of x, that's the log to the base e. If y is the natural log of x, dy dx is equal to 1 over x. If y is equal to e to the power of f of x, dy dx is equal to f dash of x by e to the power of f of x. That's the chain rule. And if y is the natural log of f of x, dy dx is equal to f dash of x all over f of x, which is the chain rule again. So here's a chain rule example. We want to differentiate y is equal to the natural log of f of x. So let's let u be equal to f of x. So y is the natural log of u, and dy du is equal to 1 over u. So that's straightforward enough. Now we need to find du dx. Well, du dx very simply is equal to f dash of x. And so dy du by du dx, that's equal to 1 over u by du dx. And that's 1 over f of x by f dash of x. And so dy dx is simply f dash of x over f of x. And that is where the rule on the previous page came from. Here's a nice exercise that you could try. Can you demonstrate to yourself that if y is equal to e to the power of f of x, then dy dx is equal to f dash of x by e to the power of f of x. Okay, so here's a second example. Y is equal to x to the power of n. Find dy dx without using the power rule. And I'm including this example because it helps, first of all, to deal with differentiation of exponential functions, but it also helps to show just how consistent the rules of differentiation are. So if x is equal to e to the power of the natural log of x, that's by definition. The natural log of x is the power to which e must be raised to give you x. And so x to the power of n then is e to the power of n times the natural log of x. Okay, and now we can differentiate. So dy dx is from the rule f dash of x by e to the power of f of x. Dy dx is f dash of n times the natural log of x multiplied by e to the power of n times the natural log of x. But n times the natural log of x is equal to n over x. Sorry, f dash of n times the natural log of x is equal to n over x from the UV rule. So dy dx is equal to n over x times e to the power of n times the natural log of x. And that's equal to n over x times x to the power of n, because we have that in red in the top line. X to the power of n is equal to e to the power of n times the natural log of x. And so n over x multiplied by x to the power of n is equal to n times x to the power of n minus 1, as we would expect. So moving on again, a slightly different view. Y is equal to a to the power of x. So this isn't strictly on the course, but it's worth looking at, in my view, because it gives another insight into the chain rule, and it's really quick and it's very powerful. So let's differentiate. Y is equal to a to the power of x. So the natural log of y is equal to x times the natural log of a. So we're going to let u be equal to the natural log of y, which is equal to x times the natural log of a. So du dy is 1 over y, and du dx is the natural log of a. So moving on from that now, the chain rule tells us that du dy by dy dx is equal to du dx. And so 1 over y dy dx then, which is equal to the natural log of a. So therefore, dy dx is equal to y times the natural log of a. And that's equal to a to the power of x times the natural log of a, because y is equal to a to the power of x. So this is short and simple, but there's a bit going on here, and it's worth thinking about, particularly this last line where I'm saying 1 over y dy dx. So the 1 over y is du dy, and the natural log of a is du dx. That's why I've got du dy in the second last line, and 1 over y are in orange, and du dx and the natural log of a are in a kind of a yellowy color there, so that you can see where they've come from. So and so that completes that section. So some more examples. So y is equal to e to the power of 4 tan x. So dy dx, very simply, just using the rule, you get 4 tan x. F dash of that is 4 sec squared x, and you multiply that by e to the power of f of x. Excuse me again. So very simply, we differentiate the 4 tan x first. We get 4 sec squared x, and then we multiply that by e to the power of 4 tan x based on the rule. What about y is the natural log of 1 over e to the power of x? Okay, so dy dx then, so is equal to, it's f dash of x. So 1 over e to the power of x, that's equal to e to the power of minus x. So when you differentiate e to the power of minus x, you get minus e to the power of minus x. So that's your f dash of x. And then that's divided by 1 over e to the power of x, and that's equal to minus 1. Now, to do this more simply, we could simply note that the natural log of 1 over e to the x is minus x, because 1 over e to the x is equal to e to the power of minus x. And so dy dx is equal to minus 1 as well. So we now move on to talk a bit about tangents. And before we get on to that, to this, let's think a little bit about what a tangent really is. And so the definition here is a tangent to a curve at some point P touches the curve at P and has the same slope as the curve at that point. Now, when that definition of the tangent may touch a curve at other points, but may not be tangential to the curve at those points. We're just talking about a tangent at a specific point. So here's a very simple example. This is a graph of y is equal to x squared. And so clearly the x-axis is a tangent at 0, 0. So I think we're all happy with that. But this is a more interesting example. Here we have y is equal to sine 2x. And so that's the green line. So that's the graph of the function y is equal to sine of 2x. And now the red line is y is equal to 2x. And the purple line then is y is equal to minus 1. Now, y is equal to 2x cuts the curve. But we can still state that it is a tangent at x is equal to 0. Because when we differentiate sine of 2x, we get 2 cos 2x. And when x is equal to 0, the value of the slope at 0 is 2. And so even though y is equal to 2x cuts through the curve, it is a tangent at that point. The second point I'd make is that y is equal to minus 1 touches the curve at many points. But we can just pick one of those points. We can say like pi over 4, and we can say at point P, which is equal to pi over 4, the line y minus 1 is a tangent to this curve. So one of the mathematical problems then that we want to solve is, given a curve and given a point, can you find the equation of a tangent to the curve at that point? So to find the equation, to do this, the first thing we do is we find an expression for dy dx. The next thing we do is we evaluate dy dx at the desired point, and we also evaluate f of x at the desired point. And so the desired equation then is y minus y1 is equal to m into x minus x1, where m is equal to dy dx. And so we can move on to an example. Find the equation of the tangent to y is equal to arc tan of x at x equal to 0. And so the reminder here, if f of x is equal to arc tan x over a, f dash of x is equal to a over a squared plus x squared. And so using that rule, f of x is equal to arc tan of x, f dash of x is equal to 1 over 1 plus x squared. Now we want to find the equation of the tangent when x is equal to 0. So f dash of 0 is equal to 1, because 1 all over 1 plus 0 to be squared is equal to 1. And f of 0 is equal to 0. The tan of 0 is 0, so the arctan of 0 has to be 0 also. And so we want the equation of a line with a slope of 1 passing through the origin. And the answer very simply there is y is equal to x. And so some other examples then. Find the equation of a tangent to the curve y equal to x plus e to the power of 2x. Oops. Find the equation of the tangent to the curve x equal to the curve of where y is equal to x plus e to the power of 2x when x is equal to 0. So f dash of x, first of all, is 1 plus 2e to the power of 2x. And f of 0 is equal to 1, and f dash of 0 is equal to 3. So f of 0 is fairly straightforward because x is 0, e to the power of 2x is 1. So f of 0 is equal to 1. F dash of 0 is 1 plus 2 times e to the power of 0. And that's 1 plus 2, and that's 3. So when x is equal to 0, f of x is equal to 1, so the point is 0, 1. F dash of 0 is 3, so the slope is 3. And so the line is y minus 1 is equal to 3 into x minus 0. And that becomes y is equal to 3x plus 1. Next example then, the slope of a tangent to y is equal to x to the power of 4 minus 1 at point P is 32. Find the point. Okay, well, differentiate first of all. F dash of x is 4x cubed. And they're saying the slope of the tangent is 32. So 4x cubed is equal to 32. X cubed, therefore, is equal to 8, and x is equal to 2. And so the point P then is 2, 15, because when x is equal to 2, x to the power of 4 is 16, and subtract 1, and you get 15. So we now move on to talk a little bit about second derivatives. So we know that when we differentiate a function, f of x, we can get f dash of x. But f dash of x is also a function, so we can differentiate that too, and we get f double dash of x. That's the f with the 2 dashes. And it's just pronounced, you can say f dash dash or f double dash. So here's some notation around it. If y is equal to f of x, dy dx is equal to f dash of x. And the second derivative, which we call d2y dx squared, is equal to f double dash of x, and so on. So I would caution you though, d2y dx squared is not at all the same as dy dx all to be squared. Here's a simple example. If y is equal to x cubed, dy dx is equal to 3x squared. d2y dx squared is 6x, but dy dx all to be squared is 9x to the power of 4, which is, as you can see, is completely different. So now we're going to talk about what I call landmarks on a curve, which will become clear as we dig into it. So here you've got a curve. You've got a point here that I've marked as a local maximum point. So a local maximum point means that point is the maximum value of that curve, generally speaking, in the vicinity of that point. Okay. The local minimum is the minimum value of the curve, again, in the vicinity of that point. Like you can see the curve, it's not the minimum value of the curve as a whole. You can see as you go to the left of the graph, the curve goes deeply negative quite quickly. Similarly, the local maximum is not the maximum value of the curve. Again, you can see on the right-hand side, the curve rises very steeply to some undetermined value. What we're talking about is the local maximum or the local minimum is it is the minimum value in the locality. So for example, looking at the local minimum, you could imagine if you had a marble and you were able to roll the marble along the curve, the marble, if you placed the marble near the local minimum point, it might roll over and back for a bit, but it would eventually settle at the local minimum point. So the the third point then we've got is the inflection point. The inflection point lies between the local maximum and the local minimum, typically. And at the inflection point, it's where you can see as we move from the local maximum to the local minimum, the slope of the curve increases gradually. Sorry, the slope of the curve gets more negative until you reach the inflection point. And from the inflection point onwards, the slope of the curve becomes less negative until when you get to the local minimum point, the slope of the curve is 0. So at a local maximum, f dash of x is equal to 0, and f double dash of x is negative. And at a local minimum, f dash of x is equal to 0, and f double dash of x is greater than 0. And at the inflection point, f dash of x is we don't care, but at the inflection point, the really important thing here is that f double dash of x is equal to 0. And then finally, not labeled on this curve, but we'll see it shortly, there is some curves have what's called a saddle point. A saddle point is a special case of the point of inflection. So at the point of inflection, we're saying f dash of x is we don't care, but f double dash of x has to be 0. At the saddle point, we're saying f double dash of x has to be 0, and f dash of x has to be 0 also. So you need to remember these rules for local maximum, local minimum, inflection, and saddle, because as you will see from some of the problems that we're going to be looking at as we move forward. Here's another sketch, which just shows this curve has 2 local maximum points. It's got a local minimum point, and it's got a saddle point. And at the saddle point, you can see f dash of x is equal to 0. Not quite so easy to pick up, but f double dash of x is equal to 0 as well. Not shown in the curve, but between the local maximum and the local minimum points, somewhere between the local minimum and the local maximum to the left of it, somewhere there has to be a point of inflection. And between the local minimum and the local maximum to the right of it, somewhere there has to be a point of inflection also. So local maximum and local minimum points can also be called stationary points or turning points. This is true for saddle points as well. It's a little bit unfortunate in my view. Reading through textbooks, you see references to local maximum points, local minimum points, saddle points, and stationary points, and or turning points. That, in my view, would make life a little bit simpler if they stuck to the same names for everything, but unfortunately they don't. So, oops, this slide is in the wrong place. I'm going to carry on, and we'll do a break at approximately 12 o'clock, or maybe a little before it. So here's an example of to find the turning points on a curve and state if they're local maximum or minimum points. So let's look at f of x is equal to x squared minus 2x plus 5. So f dash of x is equal to 2x minus 2. And so we want to find where is f dash of x equal to 0? Well, f dash of 1 is equal to 0. And f of 1 is 4 because 1 squared minus 2 plus 5 is equal to 4. So we found the x value for where our turning point is, but is it a maximum point or a minimum point? Well, f double dash of x is equal to 2 because we differentiate 2x minus 2 again and we get 2. Because f double dash of x is always positive, the point has to be a local minimum. So here's another example. What about f of x is equal to 1 minus the natural log of x all to be squared? And we're specifying that x is greater than 0 because the log of negative numbers isn't defined. So we're going to differentiate it. So, and we're going to use the chain rule. So let u be 1 minus the natural log of x. So y is equal to u squared. dy du is 2u. And du dx is equal to minus 1 over x. So dy du by du dx is equal to 2u by minus 1 over x. And that's equal to minus 2 over x by 1 minus the natural log of x. So this is 0 when the natural log of x is equal to 1. So this is, so x, for the natural log of x to be equal to 1, x has to be equal to e to the power of 1, or e. So to determine the maximum, whether it's a maximum or minimum point, we differentiate again using the product rule. So using the product rule, and this is, it's u dv plus v du, so the minus 2 over x is u, and dv is, that's where you differentiate 1 minus the natural log of x. That becomes minus 1 over x. Then it becomes plus 2x plus u, that's, sorry, plus, so du dx here is minus, or sorry, is plus 2x to the power of minus 2 by 1 minus the natural log of x. So when x is equal to e, the natural log of x is equal to 1. So the second part of this vanishes. So we're then left with minus 2 over x multiplied by minus 1 over x. And that's 2 over e squared when x is equal to e. And this is always positive. So the point E0 is a local minimum. So here's another example. The curve y is equal to e to the power of x multiplied by px squared plus 2 plus q has a local minimum at 1 comma minus 4e. Find the value of p and the value of q. Well, dy dx is equal to, so e to the power of x is u in this case, so it's u dv dx. So it's e to the power of x into 2px plus px squared plus q times e to the power of x, because when we differentiate e to the x, we get e to the x. And so, and that all becomes e to the power of x into px squared plus 2px plus q. This is 0 when x is equal to 1, because we're told that as part of the problem statement. So when x is equal to 1, 3p plus q has to be equal to 1, or sorry, has to be equal to 0. So if you look at the, just to be clear here, because I know I've, what we're saying is when x is equal to 1, this piece here is equal to p plus 2p plus q. So that's 3p plus q, and that's equal to 0. So also we know that when x is equal to 1, px squared plus q is equal to minus 4e. Okay, so the and so therefore p plus q is equal to minus 4. So and so when we combine these two, so we're combining, we're saying 3p plus q is equal to 0 and p plus q is equal to minus 4. Then we find that p is equal to 2 and q is equal to minus 6. And so one comment that I'd make, and this comes across a lot in differentiation, sometimes when you get questions like this, the actual differentiation piece is fairly easy. It really is just about knowing the rules around maximum and local minimum points. So here's another example. Then f of x is equal to e to the power of 2x minus a e to the power of x, where a is greater than 0. Show that f of x has a local minimum and find its coordinates in terms of a. So the first thing we want to do is we want to differentiate it and find if it has if it has a local. We want to get f dash of x first, find where that's equal to 0. Then we want to get f double dash of x and determine if that's positive. So f dash of x is equal to 2e to the power of 2x minus ae to the power of x. So we need to differentiate that. So f dash of x is equal to 0. Sorry, let me restart this. So we're saying f of x is equal to e to the power of 2x minus ae to the power of x. When we differentiate that, f dash of x becomes 2e to the power of 2x minus ae to the power of x. So f dash of x is equal to 0 when 2e to the power of 2x is equal to ae to the power of x. And if we divide both sides by e to the x, we get 2e to the power of x is equal to a. So to move on, 2e to the power of x is equal to a, and so therefore e to the power of x is equal to a over 2, and so therefore x is equal to the natural log of a over 2. So what we have found is that when x is equal to the natural log of a over 2, y is equal to 0. We now need to carry on and determine, is this a local maximum or a local minimum? So we're now going to we're saying that when f of x, when x is equal to the natural log of a over 2, we can see that, and this is just the workings here to go in a bit more detail of why it's 0. F dash of x is equal to 2e to the power of twice the natural log of a over 2 minus ae to the power of the natural log of a over 2. And that's simply 2a squared over 4 minus a squared over 2. And that's equal to 0. And so and that's just a reminder there, e to the power of the natural log of p is always equal to p. So e to the power of the natural log of e to the power of the natural log of a over 2, this piece, that's just equal to a over 2. And so when you multiply that by a, you get a squared over 2. And that's where this a squared over 2 comes from. And similarly, the 2a squared over 4 comes from the other expression, 2e to the power of 2 times the natural log of a over 2. So we have f dash of x. F dash of x is equal to 2e to the power of 2x minus ae to the power of x. So f double dash of x then is 4e to the power of 2x minus ae to the power of x. So we want to find out what happens when x is equal to the natural log of a over 2. And so f double dash of x is 4e to the power of twice the natural log of a over 2 minus ae to the power of the natural log of a over 2. And so that becomes 4a squared over 4 minus a squared over 2. Now, 4a squared over 4, that's equal to a squared. A squared is always going to be greater than a squared over 2, because we said up here that a has to be greater than 0, okay? And so f double dash of x is always positive. F double dash of x being greater than 0 implies that x, which is equal to the natural log of a over 2, is a local minimum. One point I'd make about this particular question, and one of the reasons I chose it here, is there's not a whole lot of differentiation goes on here, but you do need to know and understand your logs and exponentials to get this one over the line. And generally speaking, in Leaving Cert papers, particularly recent ones over the last 4 or 5 years, they're getting quite clever in asking questions that include differentiation, but also demand a pretty good knowledge of other aspects of the course as well. So finally, the answer to the question here is the coordinates are the natural log of a over 2 and f of natural log of a over 2. So let's work that out. So f of x is equal to e to the power of 2x minus ae to the power of x. F of the natural log of a over 2 is equal to e to the power of twice the natural log of a over 2 minus ae to the power of the natural log of a over 2, and that's a squared over 4 minus a squared over 2. And so the final coordinates for our question are, in terms of a, x is the natural log of a over 2, and y is minus a squared over 4. So we now move on to a question, one series of problems that differentiation can be really helpful to solve. They are called optimization problems. So an optimization problem is concerned with maximizing or minimizing some value given certain constraints. So for example, a piece of wire, you've got a piece of wire, it's 32 centimeters long, and you bend it into the shape of a rectangle. Show that for the rectangle to have maximum area, the rectangle will be a square. So in this example, the constraint is the length of the wire. We've only got 32 centimeters of wire. And the other constraint is that we have to bend it into the shape of a rectangle. So they're the constraints, they're the rules we have to work on. And we want to optimize it. And the optimization piece is where we want to maximize the area of the rectangle given the constraints that we're operating under. So let's try it. And I've just repeated the question here. So it often helps to draw a sketch for optimization problems. So here's a very simple sketch. It's a rectangle, x and y. So the area is x multiplied by y. And area varies with x. And we want to find dA dx. The perimeter is 2x plus 2y. So the perimeter is a constant. It's the constraint. So the first thing we want to do is express the area in terms of x. So the perimeter is 2x plus 2y. So y is equal to p minus 2x over 2. And the area then is equal to xy. That's x multiplied by p minus 2x all over 2. And that's equal to px minus 2x squared all over 2. And so this is, it's important to see what we did there. We started off with a rectangle with sides x and y, but now we have the entire area of the triangle expressed in terms of x alone. And in optimization questions, the first step generally is get an expression just in terms of x. So step 2 now is find dA dx. And then we're going to find the value for x when dA dx is equal to 0, because that's going to be a local maximum or a local minimum. So dA dx is equal to p over 2 minus 2x. So we're, just a reminder, we're differentiating this. So differentiate, it's a half, sorry, differentiate px, you get p, differentiate minus 2x squared, and you get minus 4x squared, but you're dividing it all by 2. So dA dx is equal to p over 2 minus 2x. And so we want to find dA dx is equal to 0 when 2x is equal to p over 2. And that means x has to be p over 4 for dA dx to be equal to 0. And so if x is equal to p over 4, then the perimeter is equal to p over 2 plus 2y. So we can see that y is also equal to p over 4. So now we know that x is equal to y. And so now we know it's a square. So that's the first piece done. We've determined that when dA dx is equal to 0, it's a square. The next thing then is it a local minimum or a local maximum? So, well, we had that dA dx is equal to p over 2 minus 2x. We had that over here. And so d2a dx squared is equal to minus 2. So f double dash of x is always negative, so it's a local maximum. And so we've proven what was asked of us. So here's another example. Now, this example is there's a bit more working in it, and I put our break in the wrong place a few minutes ago. I'd like to put the break here, and we'll do another 10 minutes. And what I'd like you to do is if you could use just a minute or two to make a sketch of this and a note of the problem, because one of the disadvantages of having to do this over Zoom is you're limited in screen space. So if you could all make a sketch of this first of all, and then we'll come back in. I want to say we'll come back at 12 o'clock exactly, and we'll continue this, and we'll definitely be on the last lap at this stage. We're on slide 50 out of 61, I think, but some of these problems take a little bit longer to work out. So I will I'll see you all at 12 o'clock. Hi everybody, welcome back. So we're now going to tackle this question, and I hope that you have a sketch of this because that will help you as we proceed. So what have we got? We've got a cylinder inside in a cone, and we're allowed to adjust the radius of the cylinder. If we make the radius smaller, the cylinder gets taller. If we make the radius larger, the cylinder gets shorter, because the top of the cylinder has to touch the cone, but the entire cylinder has to stay inside the cone. And so the first question then is find an expression for h, which is the height of the cylinder in terms of the radius. The next part is find an expression for v, the volume of the cylinder in terms of r. And then the third part is find the maximum value of v. So let's move on. So what I've done here is I've taken a cross section of the cone. So you can see the height of the cone is 12 and the radius of the base of the cone is 4. And I've on the right hand side then you can see that the height of the cylinder is h, and the radius is the base of that triangle, which is, so the h is the vertical side of the cylinder, and so there's the gap at the base between the side of the cylinder and the corner of the cone is 4 minus r. So the red triangle and the yellow triangle are similar triangles, and you can see I've marked 2 of the corresponding sides. So we know that the yellow triangle is similar to the red one, and so we can say h over 12, because they're 2 corresponding sides, is equal to 4 minus r all over 4. They're the other 2 corresponding sides, which I haven't highlighted in this diagram, but just to because I think you all would understand how similar triangles work. So very simply, h over 12 is equal to 4 minus r over 4, and therefore h is equal to 12 minus 3r. Is everyone happy with that? It's a little bit of a jump from the previous slide here. Whoops. It's a little bit of a jump from this slide to the cross-sectional diagram here. So I just want to pause for a moment, make sure that everyone's okay with that. If you have any questions, just raise your hand. Okay. So moving on, we want to find the volume then. So the volume of a cylinder is pi r squared h. And we know that H is equal to 12 minus 3R. So the volume is pi r squared into 12 minus 3R. That's 12 pi r squared minus 3 pi r cubed. So that's the second part of the question answered. We've got an expression for V in terms of R, the radius of the cylinder. We now want to find dVdr, and we want to find d2vdr squared. So remember, we want to find when dVdr is equal to 0, and we also want to determine whether d2vdr squared is positive or negative. So if we differentiate 12 pi r squared here, we get 24 pi r. If we differentiate the 3 pi r cubed here, we get 9 pi r squared, and there's a minus there. So dVdr is 24 pi r minus 9 pi r squared. We differentiate it again with respect to r. So you differentiate 24 pi r, and you get 24 pi. And if you differentiate the 9 pi r squared, you get 18 pi r. And that's the differentiation piece done, which, as you can see, is quite simple. The little bit of thought required in modeling it with the similar triangles and so on. So when dVdr is equal to 0, then 24r is equal to 9r squared. Because remember, if 24 pi r minus 9 pi r squared is equal to 0, you can divide that by pi, and you get 24r is equal to 9r squared. So therefore, 9r is equal to 24, and so r is equal to 24 over 9, which is 8 over 3. So when r is equal to 8 over 3, d2vdr squared, which is 24 pi minus 18 pi r, that becomes pi into 24 minus 48, because 8 over 3 multiplied by 18 is 48. And this is always less than 0. 48 is always bigger than 24. When you subtract them, you get a negative number. So we know it's a local maximum. Okay. Now, the last thing we need to do is find the value of the volume. So to be clear, we've found the radius. We've demonstrated that it's a local maximum. So now, finally, when r is equal to 8 over 3, V, the volume, is 12 pi r squared minus 3 pi r cubed, and that works out as 256 pi over 9. And I think we're done with this question. The maximum volume of the cylinder is 256 over 9 multiplied by pi. So here's the next question then, and I'm going to pause again for a brief moment to give you a moment to sketch this rectangle, so that you'll be able to refer back to this as we go through the question. So I'm just going to pause briefly to give you all a chance to sketch it down and make a note of the main points of the question. Okay, so what have we got? We've got a plowed field. It's 155 meters long and it's 60 meters wide. At one edge of the plowed field, you have a path which is going from P to Q. And a woman can run at an average speed of 260 meters per minute along the path and 100 meters per minute across the field. She wants to go from P to R as quickly as possible. So she will run along the path for some distance, and then she will traverse the field. She's running more slowly, but she'll have a shorter distance to travel. So the first part of the question then is, if UQ is X meters, then express in terms of X, PU, and then UR, and then the time to reach R. Okay, so as with many of these optimization questions, you need to get it all expressed in terms of one variable. In the last question, the variable we used was r, the radius of the cylinder. In this question, it's x, the distance from u to r. And then finally, once we've figured out the length of pu and ur in terms of x, and the time taken to reach r in terms of x, then we can find the minimum time. So let's start. And I've just put a brief bit of a sketch here just to remind ourselves of where we're at. So the first thing is pu is 155 minus x. And while she's running along pu, this lady is doing 260 meters a minute. And ur then, from Pythagoras, is just x squared plus 60 squared all to the power of a half, or the square root of x squared plus 60 squared. And for that length, ur, the speed is 100 meters per minute. So, and then the third piece then is, we want to find the time to reach r. We want to express that in terms of x. So the time to traverse pu is 155 minus x all over 260, because we're running at 260 meters per minute along that section. The time to traverse ur is 1/100th of the square root of 60 squared plus x squared, because we're doing 100 meters per second for that section. Okay. So the total time then is the time to get from P to U and the time from U to R. So you just add those two to get that value. And so that is the total time to reach R in terms of X. So now we want to find dt dx. So dt dx is, if you differentiate the first piece, 155 minus x all over 260. When you differentiate that with respect to x, you get, on the top line, you get -1. So that's -1 over 260. And then when you differentiate the next piece, it's you get the expression at the bottom here. And so now we know what dt dx is. And so just a couple of notes there. Time is distance divided by speed. And so we'll continue now. So we have dt dx is all of this. And we're going to simplify it a bit. So we're just going to tidy it up a bit. Multiply the 1 over 200 by the 2x, and you get x over 100. And so the t dx is equal to 0. So we take the -1/260 and we put that over on the other side. You just add 1 over 260 to each side of the equation. So dt dx is equal to 0, and so we get this. And so we multiply everything across by 260. So you get 260x over 100 into x squared plus 60 squared to the power of -1/2 is equal to 1. And then we know, we know what we're doing here to get to this point is we divide each side by x squared plus 60 squared to the -1/2. And so that means that gives us 260x over 100 is equal to x squared plus 60 squared to the power of 1/2. And so we now square both sides. So 260x over 100 is 2.6. The square of that is 6.76. So that's where the 6.76 piece comes from. And obviously the x becomes x squared. And then it becomes, so 6.76 x squared becomes x squared plus 3600. So now we've simplified it a bit. We'll carry on. So we now have 5.76 x squared is equal to 3600. And so x squared is equal to 625. And so x is 25 meters. And so remember that when x is 25 meters, this, just so we don't lose sight of things here, this is when dt dx is equal to 0, x is 25 meters. So that's we now need to determine if it's a local maximum or a local minimum. And we also need to find the time. So we had from earlier, the time is 155 minus x over 260. Plus, we've seen this formula before. So, and we now know that x is 25 meters. So we put in the value for x. And when we work that out, we get that it's equal to 1.15 minutes. It's not 1 minute and 15 seconds. When you're working with time, you need to be a bit cautious about that. You could obviously convert that to minutes and seconds if you wanted to, but it doesn't ask you to. And so, actually it does. I beg your pardon. It's 1.15 minutes, so we need to convert that to seconds, because if you go back to the original question, it says find the value in seconds. So, sorry. Ooh, what happened there? It's 1.15 minutes. And so we convert that, multiply that by 60. And that gives you the time in seconds. And that's 69 seconds, I think. There's a line missing from this, unfortunately. I'm just making a quick note so that I can fix that later. And so that's that question complete. So our next question then is the distance traveled by an object is given by 12t minus 2.4 t squared, where s is in meters and t is the time in seconds. So find the speed of the object after 1.25 seconds. So the speed is distance over time, or ds dt. So when you differentiate 12t minus 2.4 t squared, you get 12 minus 4.8 t. So the speed after 1.25 seconds then is 12 minus 4.8 multiplied by 1.25, and that becomes 6 meters per second. And the object stops when ds dt is equal to 0. So, and that's when 12 minus 4.8 t is equal to 0. So when you solve for that, you get 12 is equal to 4.8 t, so t is equal to 12 over 4.8, and that's 2.5 seconds. And so that's that question done. And so this question then, our next question, f of x is equal to x minus 1 plus 1 over x minus 1 for all real x. Explain why a line with the equation 2x plus c cannot be a tangent to the graph of f of x. So let's get f dash of x first of all and figure out what the slope function looks like. So f dash of x, if you differentiate x minus 1, you get 1. If you differentiate 1 all over x minus 1, you get minus 1 over x minus 1 all to be squared. And so that is the slope function for the curve. Now we're told the function, the line with this equation y is equal to 2x plus c. So the slope of the line has to be 2, because that's mx. And so the question we have to ask ourselves then is, why can f dash of x never be equal to 2? So x minus 1 all to be squared is always a positive number. And so 1 over x minus 1 to be squared is always positive as well. So f dash of x, which is equal to 1 minus 1 minus this, that always has to be less than or equal to 1, because what I've circled there, that's always some number greater than 0. So f dash of x is always going to be less than or equal to 1. But the slope of the line is 2. So there is no point on the curve, there's no point which has a slope of 2. And so that's why it can't be a tangent to the graph. And so that concludes today's talk on differentiation. A couple of exam tips. Knowing how to differentiate isn't enough. You need to be fluent in logs and indices and trigonometry and stuff as well. Back in the day, when Eamon and I did our leaving cert, and I dare say when dinosaurs were still roaming the earth, the leaving cert exam was structured a bit differently than it is today. So you would get a whole question on differentiation. You typically on a leaving cert paper, you might have 6 questions and do 4 or something, but each question just focused on its own individual section of the course. So you'd get a whole question on differentiation. And when you think about it, you could game it a bit, because you could game the system a bit, because you might say to yourself, right, there's 6 sections in paper 2, say, I don't like complex numbers, so I'm not going to bother doing that. I only need to do 4 questions out of the 6 anyway, so I'll know 5. And that gives me a reasonable chance of doing well. The modern leaving cert paper is not really structured in that way. They really do mix it up a bit. And so you might find a question that requires a knowledge of differentiation. You might find that popping up in 2 or 3 different places in the context of something to do with logs and indices or trigonometry. So you need to be able to use differentiation fairly fluidly in quite a wide variety of different contexts. Practice is really important, and also in the age of computers and calculators, people tend to overlook using log tables, but log tables are really, really important, particularly with differentiation. You have all your differentiation rules summarized in a single page. Really, really useful to have. And while you're practicing, try and get a more in-depth understanding. Very useful to use a graphic calculator app on your phone or PC and play with it. You can give an insight into how polynomials and trig and log functions behave. There's a website called www.desmos.com. And I also mentioned earlier, there's geogebra.com as well. They're really, really good. And generally, not just for differentiation, for many math questions, it's really helpful to use sketches and estimates. Does your answer match your estimate, or does it come reasonably close to it? If it doesn't, then that's an indicator that either your estimate or your answer is wrong, and you need to find where the anomaly is and be able to correct whatever you're doing. And if you practice that while you're studying, you'll find that using sketches and estimates can be a really powerful tool and can be really helpful. There's a whole ton of good math websites out there, and I couldn't say that any is better than anybody else. They're all each are good in their own way, and I'd encourage you to explore that as well. In an exam, it's manage your time, take a few minutes to read the paper fully, and present your work clearly. People don't think really of mathematics as communication, but if you stop and think about it a bit, it actually really is about communicating. Virtually all math is about communicating. So particularly doing a math paper, think about how you're communicating with the person who's going to read it. And so that concludes the presentation today. Does anybody have any questions that they'd like to ask, or would anyone like me to skip back to a particular slide and try and clarify something? Certainly, I'm more than happy to stay here for a couple of minutes if people would like to do that.
Thank you again, once again, to John for a very clear presentation with lots of applications and exam questions. And hopefully we'll see you next week again for the probability tutorial with Edmund Collins. Okay, so bye for now. See you next week.